honor to be here. It's an exciting thing. We love data science. We're going to hear about a lot of fun and exciting and productive projects through our next 2 days. And my job is to cause you to despair at the state of science and then show that there's hope. So, I think we as data scientists actually do a lot better than normal scientists. They're not experts at data analysis. So when I give you some of the results of what's happening today in science, you can think, oh, we do better. And we do. But we still have the issue of multiple comparisons. Our powerful tools give us a strength to look at things people haven't considered before, but they also have the weakness of trying out millions of ideas, increasing the chance that randomness will give us an answer. And then implementing a random result is way worse than not implementing a result. But the other crisis is that it's hard to implement things. So let me get started here in our brief time and show you the level of the problem and then point to some solutions. So let's see. I don't know if it's reaching over there. If you can advance the slides for me. This is how we see ourselves, right? We solve really hard problems people haven't done before. I helped discover a new drug that wouldn't exist without data analysis, because the conventional ways of doing it showed that it was not looking strong, but a fresh view from data analysis experts really made a difference. We've saved tens of billions of dollars of taxpayers by finding fraud and waste and abuse in different agencies and against different agencies, and uncovered spies and all sorts of wonderful, very hard needle in a haystack type problems. But I've found that our clients have kind of a different view of us. Like, here's some good data over here, and we have to, it's sort of a dual life. You have to scramble around in the garbage, to find those very cool results that make the difference. So it's a lot of fun. All right. So the two big problems, and again, I want to hopefully give you hope as well, but at first I need to convey the magnitude of the problems. In research, the gold standard, I've written 3 books, but it's a lot harder to write a journal article, right? Books, the publisher just wonders if anybody's going to buy them, right? The journal article has to pass through peers that pretty much don't want you to publish, that are critiquing it as hard as possible. For instance, Lancet is a major medical journal. Only 5% of the articles submitted to it are published. But they themselves believe, and of course there's a lot of self-selection in who submits. Not everybody submits, just the best. But they themselves, the editors of the Lancet, believe that only half of what they publish is actually true. They just don't know which half. And they're the optimists. They're the optimists, 50%. So most published journal articles in reputable journals, not these ego journals, reputable journals are false. Google Crisis in Science, look up John Ioannidis, a Greek-American PhD, MD. The most popular article in medical field ever is his on how it's the most read, most cited, and least followed article in all of medical. In other words, the problem continues. But he was the first to really do a fantastic job of showing how bad the problem was and what were some of the factors in different fields in terms of the hotness or things like that. Estimates are that only 10 to 40%, and again, 40 is optimist, can be replicated. In other words, the article is like a recipe, and you follow the recipe and get something very similar, at least in the same direction as the original finding or not, a vast majority of the time. How many people does this shock? Does anybody? Okay. How many people knew this already? All right, so it's a bit of a mix. There's a problem. Now, our whole field is to find findings that people haven't found before and then implement them. So it's very vital that we know how to distinguish real from imagined. Have you tortured the data until it confessed? The other problem is that a minority, perhaps about a fifth or a sixth of data science projects that seem to work in the lab actually see the light of day in terms of production. It's a horrifying statistic. Maybe you all are doing better than that. We've been at this is our 30th year of doing this, and we've gotten our stats way up. Our first decade, about 90% of the problems we tried we could solve, we thought, and only about 60% of those got implemented. In our second decade, 98% of the problems we technically solved, and 90% got implemented. So we've gotten a lot better at that. I'm only going to talk about that issue a little bit. Let's click one more. But I want to talk about the keys, just briefly in this one slide, to implementation. Change management, super important. One of the things we did is we invested in a great change management expert who's actually going to be on the panel this afternoon. So if you have, be sure to ask good questions there. But change is hard. You're telling people, let's flip the switch. Imagine a train has been running on these tracks for 30 years, everything's working fine, and you're saying, we built these other tracks. You got to switch that train over. That is a big, big deal. People are not going to do that lightly. Got to work with them from the very beginning. Work closely with the stakeholders, help them have ownership of it, be as transparent as possible to gain trust in you and in the technology. Always seek the thriving of that person. You want to care about their issues more than your own. And then lastly, deliver a professional grade software tool. We actually bought a small and an award-winning software team to help us upgrade our software deliverables to where it fits seamlessly into that system. So those are some hints on that one, and I'm going to spend most of my time on the science part. This is an example, a great study done in the psychology world. It was actually precipitated by an article that got published on ESP, extrasensory perception. Okay, and the psychologist at the University of Virginia, just a mile from where I am, said, this is ridiculous. We can't be having, that were statistically significant results of people being able to predict things ahead of time and so forth. They suspected that was due to multiple comparisons, doing a lot of experiments and cherry picking the ones that worked, which is basically what's happening in science, whether people know it or not. So they said, let's take the most popular articles. This is 2015. They took from 7 years earlier, 2008, took the 100 most popular articles in their field and tried to replicate them all. Each one, a team, not one team, but they got dozens and dozens of teams working on them. And the x-axis is the original size of the finding. The y-axis is the size of the effect that was measured when trying to replicate the result. Ideally, you would get that 45-degree angle line, roughly speaking, where things confirmed. They worked again if you did it. The green dots are the ones that were judged as replication positive. The red dots, which are the majority, replication negative, including the head of the study. One of his papers got a red dot, and they interviewed him, and he's like, well, I still believe it works. So even the head of the replication study had a hard time accepting the result of non-replication. You can see for some dots, there's a strong replication in the opposite direction from what was originally there. This study won deservedly Result of the Year for Science Magazine, and it got an award. And it's perhaps the most thorough study, certainly the most thorough I'm familiar with. All right, let's go to the next slide. I was first alerted about a decade ago to the strength of the breadth of issues involved by this Economist article going through the airport in London. And it's a fantastic article. It's still available online if you want to just type those. You have to, I always get the English wrong. I remembered how science is wrong or something, but goes wrong. That's the phrase. And it gives a great number of examples. I'll highlight just a couple that come from there and from elsewhere. We just looked at this last data point, the team of psychologists. Lancet, I mentioned. I mentioned John Ioannidis, and he believes that about 90% are false, so he and I are in that range. Amgen and Bayer, these are very important. They went back and looked at the core scientific studies that undergirded their business lines and tried to replicate them, spent millions of dollars to try to replicate those original studies, and you can see that couldn't replicate. 90% at Amgen, couldn't replicate 75% at Bayer. These are the studies on which their business is built. By the way, if you ever work in medical data analytics, anybody here? It's kind of horrifying. You never want to go to a doctor again. You're like, why are these decisions not based on, data? Yeah, statistics is actually hard to understand by doctors. You've probably seen the famous Amos Tversky result where they presented, they're teaching doctors statistics, and they present a table that says, operate or chemo for a particular kind of cancer, and they have survival rates. And then they present another group, the exact same data, but shown as death rates. And they get completely different recommendations from those two groups of what to do. So it's extremely scary. There's a lot of client education we need to be doing to help people understand. Also, how many studies are done where every error is counted equal? Did you get it right or wrong? Well, even in something as non-life-threatening as credit risk, you need 5, 6, 7 good clients to pay for one bad client. So errors aren't equal. You need to take that into account. So there's just a lot of very elementary understanding of the business problem and translating that into a technical problem that you can help your clients with. All right, let's go. So research articles like a recipe. Do this and you should get that result. And it reminds me of this Etsy. My kids are astonished they have an Etsy account. But anyway, they remind me of this Etsy phenomena called Nailed It. The original thing comes out and you try to replicate it and not so much. One other example, beautiful holiday greeting card idea. You try to replicate it. This is the state of U.S. science. So anyway, okay, so let's go to the next one. XKCD, as usual, puts it really well. There's this famous cartoon on significance. Hang on just a sec, not yet. So jelly beans cause acne. Wait, let's go investigate. And they come back and say, no, the p-value is too low. The probability that it could have occurred by chance is too high. So that sells it. But people don't give up there, right? They're all-American ingenuity. Then they say, well, maybe it's color. And they try it out. And we click one of those panels looks good. So the next day, there's green jelly beans cause acne. There was, of the 20, if we go back one, there are 20 studies, but which one do you hear about? You only hear about the positive one, right? And so you probably hear about wine being good for you or bad for you, or chocolate, or things like that. It's on the newspaper. It changes every year. Are eggs good or bad for you? What about butter? So if there were 500 studies on broccoli and liver cancer, you might hear about 2 of them and not know the other 500 exist. So there's this thing in business, in the business of science, they need to be able to record negative results and have them available so you can have a good idea of what's actually going on. All right, let's click a couple ahead. Otherwise, you're going to have these spurious correlations. So a guy named Tyler Vigin just collects one data point per year on a bunch of things and then runs these correlations. And you learn that you've got to keep Nicolas Cage out of movies because people are dying. They're drowning whenever he's there. Or, some strange link between sociology doctorates and non-commercial space launches. So anyway, how much this happens depends on if you have a lot of variables. If you have a lot of variables, much bigger chance you'll find a spurious correlation. A lot of cases, much lower chance. But the more powerful your software, the more you can torture it until something cool comes out. Just try to fit the stock market sometime. You'll get really excited until you actually use it. So I first came up with a solution to this at the beginning of our business, and it was core to getting the client to actually believe that the result was real and put real money behind it, and it was a big success for a decade. I won't be going into that, but I finally wrote it up in our first book on data science, which won Book of the Year in mathematics. That didn't make me any more attractive to women, but I am proud of it. And I called it target shuffling. And I want to briefly, in our brief time together, describe a little bit more about target shuffling, but we're basically giving it away. Like we want everybody to do this well, and we want to help in any way we can. So I'm evangelizing for there is a technique that solves half the problem. It solves the technical, analytic problem. In statistics, the key question is significance. The key question is how likely could I have gotten a result, not this result, but how likely could I have gotten a result this interesting by chance? So statistics is this weird, it's the hardest course in college. Everyone who's been to business school, it was the worst semester of your life to take statistics, right? And it's not really a math, it's more like Buddhism and calculus combined, there is an alternative reality and do this integral to get to it, anyway. So it's really, really tough. But simulation is much easier and much easier to understand, much easier to do, and much easier to get decision makers behind. You say, set up a situation where you're testing an alternative reality that's very close to your real reality, but you know that chance is underlying it. You count how many times chance does better. And you say to your decision maker, which we did when we first used it, they thought the randomness was a big deal, and we did a study and said randomness can only do so well as we did this last year on the test 1.5% of the time. And suddenly, they make a decision. I don't know anyone who's made a decision based on a p-value or a f-test value, any non-statistician that's believed in that well enough. But a simulation is easy to explain. So let me just briefly go over that. Let's assume that you're looking for, a lot of people do data cubes. They'll take their customers and slice and dice them, abstract representations of their customers, and slice and dice them into lots of different chunks of age and geography and so forth, and they'll look for a hot spot. Those are our best clients. Let's go for more of that. It's a very common thing. Well, we did this with baseball. So these are all the strike zone throws, all the pitches that went into the strike zone. The strike zone is the width of the plate, sort of from the knees to the shoulders. And then the depth, the third dimension here, is the velocity of the pitch. So this is from quite a while ago. But if you look in that set of data, the reds are the hits, where someone successfully got on base, and the blues are not hits. There are lots of different ways to not hit. But anyway, about 9% of the time are hits. Where's the hot spot? And if you search a little cube and break that into 120 different chunks and find the one that works the best, you get this result. And it has a p-value of 1 in 300. Now, what the p-value is it takes into account the proportion that's in your subsample compared to the proportion in the big sample, and the count that's in your subsample. If you had 2 out of 3 hits in a spot, that's a huge proportion, but not a lot of sample. If you had 20 out of 30, that would be way more significant. So p-value is a great way to score interestingness, but it only corresponds to a probability if you do one, an urn with blue balls and red balls in it, and you reach in, you grab a few, the p-value is a probability there. But if you do this 100 times and keep your best one, you've cherry-picked, and that p-value is not right anymore. It's way more, it thinks it's way more interesting than it really is because you've done a cherry-picking, multiple comparison, and you have to adjust for that. There are theoretical ways to adjust for that, but the best way is through simulation. So what we're going to do, if we go to the previous slide again, stare at a red point. That's a hit. Now, we're going to go to this slide. It probably changed color. See, what I did is I shuffled where the hits are. I didn't change the physics of the pitches. The pitches are all on the same, the X values are all the same, but the label on them, the target variable, has been changed to red or blue. It's been randomly changed. So we know in this world, the connection between red and location is totally random. We created a random situation. We shuffled the target variable. But there's still a high concentration somewhere. Look, there's a spot with a p-value of 0.017. We get that published in an instant. I'm going to call Lancet and tell them we got something for them. Anyway, and that's the problem. See, we looked at, there's like 40-some populated bricks, and we found and cherry-picked the best one out of it. Now, that p-value is still useful as an interestingness measure. So this is what I call a best apparent discovery. We know it's apparent because the reality is randomized, but it's the best discovery of our model given that data, and we save that. It's not quite as good as the real one, which was the first set of data, but it's still pretty impressive. Let's do this 1,000 times, shuffle, research, pull out the best, and get a distribution of those. And that's the next slide here on the right. So the red line is our real result. The blue histogram is it's in the log space, but just to make it more clear, is our distribution of randomized results. And the interesting thing to it is what proportion of the mass is better than our real one. Turns out it's 18% or so, so let's say a fifth. 1 out of 5 randomized experiments beat our real experiment. That's its true significance. Now, you're a baseball manager. Do you use this result? Chance, by the way, is always going to be a non-zero chance that chance beats you. But how does this result look to you as a decision maker? It looks really good. I mean, baseball, all sports, there's a small, when analytics was first introduced to basketball, it was estimated to add 2 points a game. And that was a big deal, so it's probably more now. But anyway, you would use this, but you'd have a very confident idea of how real it was and how likely it was just an anomaly, a spurious correlation. If you use the original value of 1 out of 300 chance, that's way more optimistic than this more realistic value of 1 out of 5 chance. So this is the key to adjusting for that hidden thing called oversearch. You've probably heard of overfit, where your model's too complex for the data. Oversearch is where you've tried so many combinations, you're going to have a spurious correlation that's going to be more likely. So to adjust for that and get honest results is a very useful thing. All right, so we'll conclude, and I think we have a little bit of time for questions and so forth. I'll just conclude that finding reliable results is tough, and getting people to implement it, which is not something you can force. We think of it as like pushing a rope, getting people to implement it is maybe even tougher. And as one of my colleagues said, most results are false, but at least they don't implement them. So how can you, I'm sure everyone here has had success in discovering real results and implementing real results, but the general issue in science is actually pretty horrible, and they need us. They need us. We can be like that. We can be an asset to anybody. The people who are writing articles in chemistry are experts in chemistry, not in data analysis, and they need us. That sort of thing. So that could be very helpful. I urge you to learn about target shuffling, and we'll be happy to. We have some resources on our website. We're here at a booth, and that's one of the tools that has proven useful over the years. And we have to remember, too, that you have to think about implementation from the very beginning and work with the person. Nobody likes a arrogant consultant, some youngster coming in with, math and having a black box that tells them to do something different the way they've done it for 20 years. So you need to go in and not have an us versus them, not the new hotness versus the old and busted, right? You need to be a part of a team and have it be partly their creation. There's a famous saying that failure is an orphan. No one will take credit for it, but success has many parents, right? And it works both ways. When something works, a lot of people claim to have done it, but also the chance of it working is better if a lot of people have a stake in it and want it to work. I mean, some of you probably have worked at some passive-aggressive, there's some technical person, you've been brought in to help, they see you as a threat. Your frenemy now is going to always be in the way of implementation. How can you turn that person into a true ally? So this requires so-called soft skills. You need some people who speak human. I've learned that. So anyway, but it can be done. So I just want to cause you to despair and then offer hope. There's a way out, and to wish everyone the best. Thank you. You can go back. So I guess there's time for a question or two. Yes? Thank you. Right. If we go back to the box in clouds, I already constrained it quite a bit. That box is a fixed box, and then there's another one that starts where that one leaves off. But if you slid the box, moved it around, you can find something. Sometimes some of those results, you're like, oh, there's this one that's on the corner that if only it wasn't there. I have 5 kids, and they're wonderful, awesome. My youngest one, she's going to get her PhD now and everything. When she was doing a high school science fair project on vegetables and electricity, she had this one result, and she's like, if I could take that out. And I'm like, no, stop. It's just so tempting, to find something. And there's always a reason to take it out, right? There's always, you can find one, a reason. So it's hard. And when people learn target shuffling, I had a young researcher in academia, you've got to get these papers out for your career. And she said, you've made it even harder now, So it's like if you're competing with somebody else to publish and you're doing it right, you've got like one arm tied behind your back in the competition. So it's going to be a hard thing. But if you're a business, Like we worked with Pharmacy and Upjohn, a drug company. They had recently merged, the two drug companies, and they were introducing a possible drug that would cost $1 billion to get all of the testing necessary, another $1 billion. They already put $300 million into it. And the question was, do we spend another $1 billion or not? And basically they weren't going to, because it was looking meh. The original, the normal way of doing statistical significance was there, but I won't go into a lot of details, but they said, can you help us look at it fresh? And we did, and we found a way to look at, they had multiple different ways of assaying it. We took all those into account. We adjusted for, it was a lot of survey results, rather than physical measurements. And anybody who's done survey work, you know that some people, they rate all their movies 5s, and other people have a much bigger scale. So when you're asking about pain or something, adjusting for that scale a little bit helps. And believe it or not, the culture in Europe and America was different with doctors at the time. Some of you might be old enough to remember when doctors were revered, and you didn't really ask questions, whereas nowadays everybody's much more interactive, probably for the good. But anyway, so the placebo effect was much stronger in Europe, because the doctor was handing you something and it was assumed to be working. It was a double-blind study. In any case, we showed that they actually had a very powerful compound on their, and so, a lot of people wonder, should I believe, and they implemented it, and I found out years later, it was one of the 3 successful drugs that that consortium of companies introduced in a decade. So it was a big impact from a small but a fresh look at things. And they made a $1 billion decision based on a couple of slides that we created. So people ask, well, what's more reliable, company or academia? If you're talking about a new discovery that the company is putting their risk behind, they're much more reliable. In fact, some medical journals require a company representative to be on the review to cover that. Now, it's possible that if they're looking for a new use of an existing product, that is a huge incentive for them to find one, and they may not be as thorough on those studies. So, yeah. You have a question? Okay. Thank you. So meta-analysis, yes, that's very good. There should be many studies on some issues. The problem is, if you're missing any, you're missing the negative results. The vast majority, they call it the file drawer effect. Somebody works on something, it doesn't get a positive result. Let's go to the slide with the matrix of dots. They don't get a positive result. Not that those dots, the earlier dots, sorry, the green and red dots at the very beginning. If you don't get a positive result, it's hard to get published. So if you go to the Science magazine study near the beginning of the talk, which has green and yellow dots on it, green and red dots, sorry. There we go. The original published studies are on the x-axis. 3 of them were red. So only 3 out of the 100 papers that were studied published a negative result. So the problem is, when these meta-analyses, the negative results are vastly underrepresented. And so you don't have the true count. So that's why if you have only a slight betterness on the published studies, you probably aren't safe. It could be easily solved. There could be a way. Don't kill trees and put it in a journal, but save a computer record of it. And then some journals are working hard to do that, but it's a long way off. All righty. Well, thank you very much. Enjoyed it.